Okay, so our next talk will be by David Reutter about biunitary constructions in quantum information, a quantum story.
Yeah, thanks for your introduction. I'm David Reutter. I'm a PhD student at Oxford, and I'm about to present joint work with my supervisor, Jamie Vickery, on biunitary constructions in quantum information. And as this title sounds a bit technical, I decided to call it Biunitary Constructions in Quantum Information, a Quantum Story, and I present it in the form of a little story. Every story needs protagonists, and in part one of this talk, quantum structures, we meet these protagonists, and we end the part with a long list of formulas. That's what we like about talks, not really. That's why there is part two of this talk, shaded tensor networks. I'm going to introduce these colorful pictures, and they are going to replace the formulas of part one. And really, you can think of this talk as an advertisement for these shaded tensor networks and their use in quantum information theory. So what are our protagonists? Our protagonists are quantum structures. An example for a quantum structure is a Hadamard matrix. A Hadamard matrix is a square, complex matrix such that every entry has modulus 1, and such that that matrix is proportional to a unitary matrix. The Hadamard matrix we all love and know is the following 1, 1, 1, minus 1. It's clearly that this is a Hadamard matrix. Every entry has modulus 1 and is proportional to a unitary matrix. But there are many, many more interesting, complicated, weird Hadamard matrices around. The other protagonists of this talk are unitary error bases. A unitary error basis is a collection of unitary matrices that are orthogonal with respect to each other under the trace inner product. So a unitary error basis is like an orthonormal basis for the space of matrices consisting entirely of unitary matrices. And the most important unitary error basis in quantum information theory is clearly the following, which is the Pauli matrices. So unitary error bases generalize the Pauli matrices. So why are these quantities our protagonists? Why should we care about them? What's interesting about them? Well, let's start with Hadamard matrices. Hadamard matrices correspond to mutually unbiased bases. And mutually unbiased bases are everywhere in quantum information theory. Many important protocols, an example here is quantum key distribution, are built basically on this idea of mutually unbiasedness. So this is a central concept in quantum information theory. Unitary error bases were first developed as a generalization of the Pauli matrices in the theory of quantum error correction. But they have many other applications. So one good example, I guess, is unitary error bases classify quantum teleportation protocols. And they also classify dense coding schemes. So again, unitary error bases pop up everywhere in quantum information theory. I would even go as far as saying that as soon as we have a quantum protocol, which is somehow built on entanglement, then it's quite likely that at the mathematical heart of this protocol, there's one of these quantum structures. So there's definitely enough incentive to understand these quantum structures, to understand the space of all these quantum structures, to understand how these quantum structures interact with each other, to understand how wild they can really get, how crazy and how different from these examples I've been showing you in the last slide they are, or just simply to classify them. But that's a really hard task. They are actually known to be really, really hard to classify. Hadamard matrices are classified up to dimension 5, and they have been around for quite some time. The general structure of unitary error bases is virtually unknown. You just have no idea. In dimension 2, they're all equivalent to Pauli matrices, but in dimension 3 or higher, anything goes. Nevertheless, there are several known constructions of unitary error bases and Hadamard matrices. So just to do some name dropping here, probably the best known constructions, which give an example of what I'm going to talk about, is Dieter's construction from 2004, which is a construction of Hadamard matrices, or Werner's quite famous shifter multiply construction from 2001 for unitary error bases. All these constructions have like a common ground, a basic common idea. And this idea is that you use quantum structures and take them together to obtain new quantum structures of higher dimensions. So what do I mean with this? Let me just give an explicit example, coming to our slide full of formulas. Let's think about constructing Hadamard matrices. We can take, for example, two Hadamard matrices A and B, and just take the tensor product. The index expression is written here. The resulting thing is again a Hadamard matrix. You can pretty much see that every entry has modulus 1, and you can easily check that the corresponding matrix is unitary. So that's all simple and clear. We can slightly generalize this formula as follows. If I write B superscript C, I mean it's a list of Hadamard matrices. So B superscript 1 is a Hadamard matrix, B superscript 2 is a Hadamard matrix, B superscript 3 is a Hadamard matrix. So really this tensor BC, BD is really a list of Hadamard matrices. And if I take them together in this way, the resulting thing is again a Hadamard matrix. That every entry has modulus 1 is again straightforward and easily to be seen here. That it's unitary, not that obvious to me just from the formula, but obviously you can just write down the unitarity equation and check that it holds. Similar equations, similar formulas hold for the construction of unitary error bases. The best example or well-known example is the following, where we just take a Hadamard matrix A, and from this we can construct a unitary error basis as given in this formula. This construction can be generalized to the following. Here we take three different Hadamard matrices, A, B, and C, and basically apply the same formula. And we again get a unitary error basis. But we can write down different constructions like the following. Here we take a family of Hadamard matrices, A superscript B, and two unitary error bases, and construct a unitary error basis of higher dimension. Or let's go even more crazy and write down the following formula, where we take four Hadamard matrices and a unitary error basis to construct a unitary error basis in quite a high dimension. For this last construction, I invite all of you, if you're very motivated and maybe a bit bored, to really prove that this actually defines a unitary error basis, to prove that this formula is unitary and that the different UABCs are actually orthogonal with respect to each other. And I tell you, it's not easy to show that. It's a straightforward calculation, but it will take some time. And there are more formulas of that form. But so not the question of proving these equations is interesting, but really more like, where do these equations come from? Why do they work? How can we come up with them, right? I've just written down a list of index expressions and told you, yeah, you know, you can check it's a unitary error basis, but really, why am I doing this? Like, how do you come up with these constructions? Do we just sit down and write down index expressions in a long list, and just some of them might work, others might not work? So far, it really has been basically ad hoc calculation. And I'm going to present you a way to think of these equations and to think of these structures that basically lets you come up with all these constructions in a very nice and simple way. And that helps you kind of understand the space of these quantities. So yeah, the main question here is what's going on? So let me give two more comments about this slide before I move on. Firstly, it should be noted that only the first three constructions on this slide have actually previously been known. All other constructions on this slide are new. And secondly, the constructions are logically independent, so I'm not cheating you here and I haven't just taken one construction and iterated it 20 times and written it out in a weird form. So these constructions don't imply each other, they're like logically independent from each other. Right, so that's our mystery. Where do these constructions come from? How do these structures behave with respect to each other? And to understand this mystery, we have to go a step back and go into new territory to understand what's going on. And that leads me to part 2 of my talk. And this part 2 is about a new setting, and this new setting is planar algebras. In 1999, Vaughan Jones, famous for his Jones polynomial, introduced the theory of planar algebras. And planar algebras, in a very, very rough sense, is about diagrams like the following. It's like nice, colorful diagrams. Planar algebras have many names. For example, they are basically equivalent to higher category theory. That's the direction I come from. But they are also a special case of planar algebras are tensor networks. And we all have heard of tensor networks today and the other days. Planar algebras have many, many applications. In mathematics, they are very important for the classification of subvectors in operator algebras, or for the classification of fusion categories. In physics, they are used in statistical mechanics, in topological quantum field theory, in string theory, in condensed matter theory, while then I'm suggesting we should also use them in quantum information theory. Why am I suggesting this? What is the basic idea here? There's a concept which was invented by Jones actually in his original planar algebra paper called biunitarity. And I propose that we can use this concept to solve our mystery of these quantum constructions, or at least to better understand this mystery. I mean, solving is a strong word. So what's going on? What is the planar algebra? What am I talking about here? To understand what planar algebras are, or how we can use planar algebras as quantum informationists, let's go back to talk about tensor networks. Tensor networks have the following graphical components. We have vector spaces, which are represented by wires. We have the vertices represent linear maps. So brief comment here is that time runs from bottom to top for me. So a linear map from V to W is depicted as is shown here. And vertices with many legs basically correspond to linear maps between tensor products of vector spaces. And we can put these components together in a tensor network like the following. And such a tensor network, such a contraction of linear maps, just corresponds to a composed linear map. In this case, a composed linear map from the vector space E tensor F to A. And here on the left, I've written a little legend to kind of so that we can see what's actually going on. Right, so let's suppose we have the following situation. We don't just want to talk about one tensor network. We really want to talk about a family of tensor networks. So let's suppose we're in the following situation here. All these tensor networks, this is a family of tensor networks labeled by I and J. They are all of the same form, but they involve different vector spaces and different linear maps. So really, if I vary over I and J, I just get a bunch of tensor networks. And I could write them down in a list if you want. And they all look the same, but have different ingredients. So let's suppose we want to argue about these structures as a family of tensor networks. I will now introduce a graphical component to this calculus, to the calculus of tensor network. I will extend it such that we are able to talk about these families of linear maps in a unified, in a simplified, in one picture, basically. So I'm going to draw pictures like the following. On the left, I again have a little legend and I talk you through it, what every component here means. The shaded regions really correspond to indexing sets. So the blue region corresponds to an index I. The red region corresponds to an index J. Wires between two regions correspond to family of vector spaces labeled by the adjacent regions. So here, this wire on the bottom between the blue and the red region is a family of vector spaces labeled by I on the left and J on the right. Right? The wire on the bottom right, the wire which is labeled by Fj, labels a family of vector spaces labeled by the adjacent red region labeled by J. And the same is true for vertices. Vertices correspond now to family of linear maps labeled by all adjacent regions. So overall, such a graphical picture really corresponds to this family of tensor networks. So I have this family of tensor networks, and I can turn it into this picture. And if you see this picture, you know how to translate it back into this family of tensor networks. Right? So the thing I'm proposing here, or I'm introducing, is this notation where we can say these two-dimensional pictures with shaded regions correspond to families of tensor networks and the other way around. So we can go both ways. So in some sense, you can think of this really just as a slick, nice, or not so nice, whatever you prefer, notation. And as always with notations, we have to show that these notations actually make sense, that they are useful, that they are not complicating what we're doing, but that they are simplifying. And that's basically the point of this talk here. I want to show that using this notation, we can get a grasp on a certain kind of structural behavior in quantum information theory, which we otherwise probably wouldn't have gotten. So now that we've introduced these shaded tensor networks, we can also think about specific tensors in these shaded tensor networks. And I want to consider a very simple kind, if you want, a very simple kind of equational tensor, and that's a biunitary. So biunitary for me is a 4-valent tensor. It's a tensor like the following with 4 legs. That fulfills these 2 equations, or these 4 equations. The first equation set is unitarity. For those of you who have some experience with tensor networks, it's basically the same unitarity equation we know. We take the tensor, compose it with its adjoint, and it's the identity of this specific type, and the other way around as well. I've purposefully written this as vertical unitarity because there's a sense of going from bottom to top. But since we're drawing 2-dimensional pictures here, we could also ask for horizontal unitarity. So if you just turn around our head, it becomes the same vertical unitarity equation, just as in a horizontal way. So to note here is that it's only horizontal unitary up to a scalar, but that scalar is not too important. It's similar to the situation with Hadamard matrices, where every entry has modulus 1, but the matrix is only proportional to a unitary. Right, so what do these biunitarity equations really mean? What are they about? Well, we can translate it back into families of tensor networks. Then this U really corresponds to a family of linear maps labeled by red, blue, and green, and yellow, labeled by the red, blue, green, and yellow region. And this family of tensor networks fulfills certain equations, for certain algebraic equations, right? And if we introduce algebraic equations, we have to ask, what are they good for? What are they talking about? And that brings me to a surprising connection. These algebraic equations, these biunitarity equations, they correspond precisely to the equations defining our quantum structures. Actually, back in 1999, in his original planar algebra paper, Jones noted that Hadamard matrices are biunitaries of the following type. So this is, again, just a family of tensor networks in this graphical calculus. I have to specify certain regions and certain wires. And then the equations which tell me that this tensor is a biunitary exactly correspond to saying that the corresponding family of tensor networks is a Hadamard matrix. So Hadamard matrices are in one-to-one correspondence with biunitaries of this form. The data of a Hadamard matrix is precisely determined by being a biunitary of that form. So now biunitarity is asking about vertical unitarity and horizontal unitarity. So the notion is inherently symmetric under basically tilting our head by 90 degrees. Right? So if we have a biunitary and tilt our head by 90 degrees, it's definitely, again, a biunitary. So really, if we look at this picture and tilt our head by 90 degrees, we see the following picture. So these biunitaries are also Hadamard matrices. Now that's a certain symmetry in the construction I'm describing here. So those are Hadamard matrices. In 2012, Vickery showed that unitary error bases are also biunitaries, but this time of the following type. So the difference between Hadamard matrices and unitary error bases, you can think of it as just a different type, but it's the same equation. It's the same biunitarity equation. Hadamard matrices are, if you want, left-right shaded biunitaries. Unitary error bases are only shaded on the left, and they just have normal vector spaces as wires and no families of vector spaces there. Another important biunitary which I'm going to need for my construction, first of all, we can obviously again tilt our head by 90 degrees, and these things also correspond to UVs. So the last component I'm going to need for my constructions, and that looks a bit more complicated, is families of Hadamard matrices. So if I say family of Hadamard matrices, I again mean the lists of Hadamard matrices I've been describing in the second slide, these index lists. A family of Hadamard matrices corresponds to a biunitary of the following type. So here this picture is 3-dimensional. So I have the blue region in the rear and the yellow region in front. The different colors are not really important. So there's no mathematically like reason why I use different colors. It's just easier to read the 3-dimensionality from the picture here. So you can think of this type as basically being the type of a Hadamard matrix, but with an additional half-plane sheet, with an additional yellow half-plane sheet attached. And I can attach the sheet along any direction really I want. And I can also attach it to the rear or the front of the Hadamard matrix, so that doesn't make a difference. So these are our basic quantum structures, and they correspond precisely to biunitaries. So if you want, the biunitarity equation we have seen unifies these quantum structures. So what can we do with these things? Why are they useful? Why is this a useful perspective? So suppose we have two general biunitaries of this form. Then we can join them or contract them together along a diagonal, like this. That obviously only works if the types match. And the result is again a biunitary. Well, why is that true? If you have some experience with tensor networks, you pretty much see that this is again unitary. It's just you just compose it with this adjoint and it all works out. But then if you tilt your head by 90 degrees, the picture looks pretty much the same. So it's also horizontal unitary. So given two biunitaries, we can compose them diagonally to obtain another biunitary. We can also compose them along the other diagonal, obviously. So there's no good chosen diagonal. So what do we know now? We know that quantum structures are biunitaries, and we know that we can compose biunitaries. So the logical next step for us is to compose quantum structures. And I'm going to do that now. So here on the top of the frame, I've shown the types of biunitaries we are interested in: Hadamard matrices, unitary array bases, and families of Hadamard matrices. And I'm going to show you the following construction. So what happens here is A is a family of Hadamard matrices. Right? You can compare it with the picture on the top right. It's exactly the same. B is again a family of Hadamard matrices. This time the half-plane sheet is just attached along a different diagonal. So what's the resulting overall type? The resulting overall type is a picture with two shaded wings. It has a shaded left wing and a shaded right wing. The wing is basically yellow in front of blue, but we can think of this just as a sandwich color. It's just a new color, yellowish blue, purple maybe. This is similar to in tensor networks. If we have two vector spaces, we can either think of it as two wires next to each other, or we think of it as a thick new wire if you want. So the overall type of this thing is the type of a Hadamard matrix. So what we have done is we've taken a controlled family of Hadamard matrices, thought of them as biunitaries, composed them together. The result will have the overall type of a Hadamard matrix, and we know it's a biunitary. But biunitaries of this type are Hadamard matrices. So what happens here is that we have written down a construction for a Hadamard matrix from two controlled families of Hadamard matrices. And we can actually write down the index expression for this construction if we again use this translation into families of tensor networks, and that's the following expression we've seen on slide 2. So let me give another construction. Here we take a Hadamard matrix B, another Hadamard matrix C, and a third Hadamard matrix A. And the overall type of this thing, if you again compare it with the first row of pictures, is a unitary array basis. So what we've done here is we've constructed a unitary array basis. And the corresponding formula, if you again translate these pictures into tensor expressions, is the following. And we can go on like this. For example, we can look at the constructions like this. So it's not important here that it's really clear how these are composed together. Those are a bit tricky. But in principle, it's again the same idea that we take biunitaries and compose them diagonally with each other. Here, I've introduced another biunitary, which are quantum Latin squares. A quantum Latin square is a square grid of vectors, such that each row and each column is an orthonormal basis. So this is also a quantum structure that's a biunitary of a different type, and we can use them in these constructions to kind of enrich our space of constructions. But it's not really important. You could also drop them, but then you just have less constructions. And those are just families of constructions we can make. So those are all constructions that work, and you can basically play this game, just write down a huge lattice of biunitaries, compose them together in all kind of weird ways, and it still works, and will still give you, in this case, unitary array bases. We've also used the construction here on the bottom left to actually construct an actual unitary array basis. So we've chosen Hadamard matrices and just written down a unitary array basis, an 8 times 8 unitary array basis, and we've proven that this unitary array basis cannot be obtained from any of the previously known constructions. So that really gives us new structures, new quantum structures. Right, so what have we done? In the actual paper, we have classified quantum structures in terms of biunitaries in shaded tensor networks. So we've unified this notion of quantum structure. We've then composed them By doing this, we've obtained a simple graphical calculus to come up with many new constructions involving Hadamard matrices, unitary error bases, and quantum Latin squares. So you can really think of this graphical calculus as some kind of Lego. You really have these basic building blocks, you glue them together in all kinds of funny ways, and the result, if the type is right, so it's just a matter of type checking, if the resulting type is the correct one, you know that you'll get a construction which gives you a new unitary error basis. And we have shown that these constructions actually give rise to new unitary error bases which cannot be obtained from any of the previously known methods. So I hope I got you a bit excited into shaded tensor networks, and you've seen that they might really be useful, and they might be a useful extension of the theory of tensor networks. If you want to know the full story, or if you want to see a 4-page long list of 64 8x8 matrices, that's the actual unitary error basis we've constructed, but you can also skip over it. Then have a look at our paper. And since I still have some minutes left, I would briefly like to comment on how these results might play a role in the classification of unitary error bases. So what we've seen is that we basically now have a scheme for constructing new examples of UEBs. And these new examples are far more exotic than the examples that have previously been known. So to prove, in our case, in our paper, that the new UEB we've constructed is actually more general than the ones that could have been constructed from earlier constructions, we've basically used this exoticness. We've used that this UEB doesn't fulfill certain niceness properties, if you want. Also, something we should take away from this is that we expect more examples of UEBs in composite dimensions, because many of the constructions we've presented here actually use UEBs in composite dimensions. And that's very similar to the case of Hadamard matrices. So it's well known that because some of the Hadamard constructions were already previously known, that there are more Hadamard matrices in composite dimensions. It's not a coincidence that Hadamard matrices have only been classified up to dimension 5, and then in dimension 6. You have 3 times 2, and they are complicated 3-dimensional Hadamard matrices, so you have no idea what's going on in dimension 6. So our research also suggests, from what I've been saying, that we should probably consider UEBs in the larger context of all biunitaries. So we shouldn't consider UEBs as something and Hadamard matrices as something else. We should consider them as one big concept and like special cases of one and the same larger concept. And yes, so that's it from me, and I hope you enjoyed the talk, and I thank you for your attention, and if you have any questions.
Right, questions? Well, I'll start with a question which is probably a very naive one. You started with a mapping between planar diagrams and tensor networks, but it seemed that in your constructions you departed from this planar
Right.
structure. So,
Right.
Is the actual class of diagrams that you're working with some kind of broader class?
Yes, it's not. So the name planar is probably misleading, because the people who invented these planar diagrams actually wanted to consider them as planar diagrams, but you can consider non-planar diagrams, and that's what we do. So we have really 3-dimensional diagrams here. But that's all right, because if you look at the actual translation, which is here, there is nothing which prevents you from using non-planar diagrams here. It's still, like, the translation still goes through. There's nothing telling you, this has to be planar. Yeah.
So you have introduced 3 or 4 different types of biunitaries,
Yeah.
Based on the different kinds of colorings that you can have. Are there other kinds of biunitaries you can get by fiddling around with which colors you make, and are any of those known structures already? And sub-question, are there any that aren't known structures that could be interesting things to look at?
Yes.
That are just suggested by this?
Yeah. So we have these structures. Then, as I said, we have these quantum Latin squares that also correspond to biunitaries. But then you could, as you said, you could basically write down different types. And these types still lead to constructions of unitary array bases, and these correspond to weird unitary-like structures, weird matrices with block form, which have some properties. And we can actually write them down, and that's something we've been looking at, and we might fit that into a paper. So you can actually write down new quantum structures, which you can also use for UEBs. But definitely the simplest and kind of easiest to understand structures here are really Hadamard matrices, UEBs, and these quantum Latin squares. But yes, yeah, you can definitely look at more complicated biunitaries. And we probably should at some point.
Other questions? Yeah, there's one in the back there.
So you said that you gave a classification, but what was the equivalence relation?
Right, so I definitely didn't give a classification of UEBs. That's like a really open, hard problem. There is an equivalence relation of what to, which classification did you mean?
Well, at the end, you have a slide that you classified all these. Yeah, could you get the last slide, if that's possible? Classified quantum structures in terms of biunitaries in shape.
Right. That's
so
not
what's the equivalence relation in this?
Right. So here it's not classified in the sense of there doesn't need to be an equivalence relation. So here it's really, if you just write down the biunitarity equation, that just gives you an tensor expression. And this tensor expression is just saying it's a Hadamard matrix. So up to equality if you want. There's no equivalence relation. Right?
And my second question is that imagine I give you a biunitary with many input and output legs.
Mm-hmm.
Do you have a way of decomposing it into
other
simpler
biunitaries?
biunitaries? Or?
Yes, that's a good question. No, there's no obvious way to do it. There are definitely, so for these constructions, if you pick a specific construction, then if you say compose 2 Hadamard matrices or 3 Hadamard matrices to get a UEB, then this UEB has certain properties which you can check or at least can see, that definitely doesn't arise from such a composition. But these kind of questions are exactly what is going to be important in a classification of UEBs, to say, if I have a UEB, is it of this composed type? Is it a generic UEB which doesn't arise from a composition? So this is exactly the important kind of questions we have to ask here. But I don't expect that there's like a graphical answer to it. It probably really depends on the specific cases you consider, and it will be like hard linear algebra.
Other questions? So you do these constructions by constructing these diagrams, but do you have a systematic way of actually enumerating all of the useful diagrams?
Yes. So in the paper we have a list of all compositions we can write down which only use 2 or 3 biunitaries. So actually, the first 2 constructions here, they look a bit weird, and that's because they are in this list. So those are actually like the most general things we can do with 3 biunitaries. But we have stopped after 3 because then it gets pretty hard, and there are quite a lot of solutions there. But you could, in principle, work out a way. You can basically just take the biunitaries, as soon as they fit together, you compose them together, and you just see whether you get the type of a UEB out of it. So in principle, it works. There is probably some nicer algorithm there than just this enumerating that we've tried. But yes, that's also an important question, yeah.
Other questions? All right, well, let's thank David again.